Welcome. In this video, we'll be talking about thermodynamics. Now, most students find it very difficult to understand the basic concepts of thermodynamics. So I've taken the pain to present to students step-by-step approach to understand basic knowledge, to help us to have basic knowledge of thermodynamics. Now, students who are watching me today, if you think thermodynamics is difficult, then watch this video. By the end of this video, you'll be able to know or appreciate that thermodynamics is simple. I was once a victim, but now I've overcome. I'm not saying I'm perfect, but I've overcome. So please don't stop tuning in to my channel. Visit my channel regularly and subscribe as well, so that every update on thermodynamics you'll be able to get it, or mathematics as well. Now, thermodynamics is a branch of science that deals with the relation between the properties of a system, or properties of matter, or properties of a substance, and the quantity heat and work which causes change of state of that substance. Now, thermodynamics, it is the branch of engineering science that deals with the effect of heat and work transfer upon the properties of matter or substance. Or it can be defined as the branch of science that deals with the relationship or relationships between work and heat and the properties of a system, and the conversion of heat energy to work energy by means of a heat engine. Now, a heat engine is a name given to a system which, by operating in a cyclic manner or going through a cycle, produces net work from the supply of heat. A heat engine, for example, can be the internal combustion engine or a lorry engine, which uses fuel, petrol, diesel, and other fuels, liquid fuels or gaseous fuels. It can also be a steam engine. So heat engine is basically a diesel or petrol engine or gasoline engine, any liquid fuel engine or gaseous fuel engine, as well as a steam engine, a steam power plant that generates or that converts heat energy to work energy is an example of a heat engine. Now, so thermodynamics is just basically the conversion of heat energy to work energy. Now, we have to explain some properties, some things about thermodynamics for you to appreciate thermodynamics. Now, in thermodynamics, we have what we call a system. In the definition of thermodynamics, I use the word substance or matter. We can equally use the word a system. So, if you are talking about thermodynamics or thermodynamic system, we are only talking about fluids. Thermodynamic system or a system in general is a certain collection of matter in a prescribed or arbitrary prescribed region. It is a certain collection of matter in an arbitrary prescribed region. Now, a system can be covered by or can be enclosed by something or by a surrounding. So whatever surrounds a system is called surrounding. Whatever surrounds a system, we call it surrounding. A system is a certain collection of matter in an arbitrarily described region. Now, a system is surrounded by the surrounding. And we also have something which separates the system from the surrounding. We call it the boundary. Let's take for, if you have a container or a saucepan, a bowl, containing water. Now, what is inside the bowl? If this is the bowl, the inner surface of the bowl, this is the bowl or the soft one, which is covered. Now, which contains water. There is water inside this soft one. Now, matter, we say matter is anything that has weight and can occupy space basically. And we have the basic three states of matter, which is solid, liquid, and gas. In thermodynamics, when we talk about a system, we are talking about a fluid, liquid, or gas, liquid or gaseous matter. So what is inside this bowl is what we call a system. Now, this bowl is covering the system. It's covering the system, which is the water. So this wall that contains or that covers the system is what we call the boundary. This wall that separates or that comes into contact with the system, we call it the boundary. So we call this surface, the surface here, boundary. So boundary is a surface that separates the surrounding from the system. So what is surrounding? Surrounding is anything that surrounds any space that surrounds the saucepan, that surrounds the saucepan, or that surrounds the system. So the wall here is a surrounding. We can also see, if you are talking about, since we are talking about fluid, we can also see that the air surrounding the saucepan is the surrounding. The air surrounding the saucepan is the surrounding. So the surrounding is anything here. Anything here within this region, anything. So we have the system and the surface that separates the system from the surrounding. This surface, which separates the system from the surroundings, is called boundary. And what surrounds the system is what we call surrounding. So system basically means a liquid or gaseous matter. Now, in thermodynamics, when we talk about a system, like I said earlier on, then we are basically talking about fluids, liquid or gaseous matter. So we've known what a system is, we've known what a boundary is. Now we also know what the surrounding is. Now we should be able to know all these things so that when we are talking about we made mention of any of these parameters or any of these terms in thermodynamics, you'll be comfortable with or you'll be able to understand. Now, in thermodynamics, we have properties or when we talk about matter, we have properties of matter. Now, so also we have properties, thermodynamic properties of a system. Now let's talk about thermodynamic properties of a system. Thermodynamic properties of a system. Now, from this diagram, we want to establish how or what qualifies to be a thermodynamic property of a system and what disqualifies to be a thermodynamic property of a system. If you have a graph of this, you have these four graphs, this, that, and that. Four graphs. We have four graphs here. So we have this graph, this graph, this, that, and that. We have four graphs. Now, let's assume that we have pressure on the vertical axis. So let's see whether pressure qualifies to be a property of a system or not. And this is the initial state of the system, and this is the final state of the system. Now, if we have a pressure of 7 bar at this level, 7 bar or 700,000 Pascal at this point, 7 bar at this point. Now, the pressure 7 bar at this point on this curve will be the same at this point on the second curve. So the pressure along this horizontal line, along the horizontal line here, will be the same throughout. Which means that regardless of the path the fluid passes to reach, from starting from the initial state to reach the final state, regardless of the path the fluid passes to reach the final state, pressure does not depend on that graph. Pressure at this level will be the same for this curve, will be the same for this, will be the same for this, and will be the same for the last. So pressure is independent on the path the fluid passes from moving from the initial state to the final state. So pressure is a property of a system. Let's say we have volume on the vertical axis, or we have pressure here, 7 bar. We have volume on the horizontal axis, volume. Now, if you want to measure volume at this point from the reference O, volume at this point, if the volume at this point is 2 meter cube, now volume remains the same vertically parallel to this vertical axis. If the volume from here to here is 2 meter cube, it means that volume along this line will also be 2 meter cube at all times. So volume at this point will be the same as volume at this point, will be the same as that, will be the same as that. So volume does not depend on the path as well. So volume of the fluid does not depend on this path. the fluid passes to reach the final state. We can also have the volume here 3 meter cube. We can measure the volume here 3 meter cube. The volume along vertically above this 3 meter cube, vertically above 3 meter cube, as well 3 meter cube. So we can have the same 3 meter cube vertically along the vertical axis, which means that the distance from here to here is 3 meter cube. From here to here is 3 meter cube. From here to here, this side is 3 meter cube. So volume does not depend on the path. We have the same pressure, just at the same pressure, regardless of the path, the same volume. So volume is a property, thermodynamic property of the system. Now, let's look at another property, temperature. If we compress the gas, I'm using this from the beginning because if we heat a fluid, if we supply heat to a fluid, pressure changes, volume changes, the temperature also changes. That means pressure rises, temperature rises, volume of the fluid also rises. If you supply heat to it, volume increases. Now, so temperature, let's try temperature. If you have a diagram, also the vertical axis or the horizontal axis having temperature, let's say 2 degrees Celsius. If you have temperature on this axis, 2 degrees Celsius, on the temperature scale, if you have 2 degrees Celsius along this line at this point, we also have the same temperature. If we supply the same quantity of heat to to the same fluid, if you try to pass through another part, we will also have the same temperature of the fluid. Or if you try to reduce the temperature, if you try to reduce the heat supply such that the graph trace here will be different from this, then when the fluid rises to a certain temperature, when the fluid rises to this level, when you draw the curve to this level, or when the path trace reaches this level, the temperature here coincides with the temperature from the first graph. If we supply heat here rapidly for the fluid to reach this point at a fast rate, and we also supply heat slowly for the fluid to delay in reaching the final state, then it means that definitely the fluid will reach this temperature. Whether you supply more heat or less heat, if you want it fast or you want it slow, still the fluid will reach that temperature. So whether slow or high heat is supplied, we will still attain that temperature. Even though the second one might delay, the less heat supplied would delay the graph or would delay the temperature, but the same temperature will be attained. So the temperature at the same level, this level will be the same as the temperature at this level throughout. So temperature will also not depend on the path the fluid passes to reach the original state. It can follow this till the fluid will reach that temperature. If you follow this graph, the fluid will reach that temperature. So temperature also qualifies to be a property, a thermodynamic property of a system. Now, if we talk about internal energy of a fluid, or the energy of the fluid, the molecular energies, the energy gained by the molecules of a fluid, now, when heat is supplied to a fluid, the molecules gain energy. Now, the level of energy gained by the molecules will depend on the amount of heat supplied. The rate at which the heat is supplied. So if the heat is supplied at a faster rate, water will boil faster. So the molecules will be agitated at a faster manner. Now, if the supply of heat is slow, it means that we are going to get the same internal energy. We will still get to that level of energy, but it will take time. So if the initial one was supplied at a fast rate, and then we have an energy of 2 Newton meter or 2 joules, and then we also supply heat at a slower rate, and then reach a level of for it to reach the same level, but it takes longer time for it to reach there. So what we are trying to establish here is that no matter how slow you supply the heat, no matter how fast you supply the heat, the energy to energize the molecules will still be attained. That same level will be attained, whether you supply slow heat or rapid heat. So it means that the internal energy of the fluid will also increase to reach that level when you supply slow heat or less heat. So internal energy qualifies to be a thermodynamic property. Internal energy. Again, according to the first law of thermodynamics, we have other properties like density of the fluid and so on and so forth. But the thermodynamic properties is what we want to emphasize on. We have other properties of the fluid. So we also have enthalpy. So the enthalpy of a system, of a fluid, will also be independent on the path the fluid passes to reach the final state, which we will establish later. Then entropy. Entropy also is independent on the path through which the fluid passes to reach the final state. Now, so these are thermodynamic properties of a system. The 6 thermodynamic properties of a system. Now let's look at, if you have the same graph, If you have the same graph from 1 to 2, we have pressure here, we have volume here. Now, let's look at, first of all, work done. Work done, we say work is a product of pressure and volume. Work done depends on pressure and volume. And we have established that pressure and volume are thermodynamic properties. Now, which means that work done in thermodynamics is the area under the curve. So work done, pressure times volume, is the area under the curve. So work done is the area under the graph. Work done. So if work done is the area under the graph, then it means that for the first graph, 1, the area under this graph will be this. So we have this area for the first graph. If you look at the second graph, The second graph will have more area than the first. So if you go beyond the second graph, it means that the higher we go, the more the area, which means that the work done or the area under the graph depends on the type of graph we draw. So because you have drawn this hyperbolic graph, then it means that if we have a straight line graph and compare it to this hyperbolic graph, it means that the straight line graph using the same initial and final points will have more area than the hyperbolic graph. So it means that work done depends on the path the fluid passes to reach the final state. So work done is not property of a system. Work done is equal to pressure times volume, which means, and because work done is the area, it means that work done depends on the type of graph. Since work done depends on the type of graph, then it means that work done is not a property. Let's look at another quantity we mentioned in the definition of thermodynamics: heat. Heat, according to the second law of thermodynamics, is written as the product of temperature and the change in entropy. So heat is also, or the change, this is change in work done or change in heat. Change in heat or heat is also depends on the temperature and the entropy, which means that temperature, heat is also employing temperature and entropy. So this also giving you area. So it means that if you draw a graph of TS on a TS diagram, we are going to get heat. On a PV diagram, we'll get work done. On a PV diagram, we'll get work done. On TS diagram, we'll get heat. So it means that under this TS graph will give us heat, which means that heat depends on the graph or the line trace from the first initial point to the last point. So heat is not a thermodynamic property of a system because heat depends on the path. If you compare the linear graph to this hyperbolic graph, it means that the linear graph the area under the linear graph will be more than the area under the hyperbolic graph. So it means that heat increases as, or the increment of heat depends on the type of graph you draw. And the greatest of all the area will be the last one here. So the greatest of all the work done on the PV diagram will be this. Things that will have the greatest area. So the thermodynamic properties of a system are pressure, temperature, entropy, internal energy, volume. I mentioned 6. Now let's conversion of heat and work. Let's talk about sign conversion. For heat and work. We know that the pressure in the system can reduce, volume of a system can reduce, volume, pressure, temperature, enthalpy, internal energy, they can reduce. Fine. Now let's look at the sign conversion of heat and work. If you have this system, now we are going to talk about one school of thoughts conversion. Now, from this first introduction, I will talk about one school of thought way of approaching or the sign convention used by some schools. Now we have heat into a system, Q into a system. We have Q from a system to the surrounding. Heat supplied from the surrounding to the system, and heat from the system to the surrounding. Now, if heat enters the system, I'm using one school of thought, philosophy or sign convention. So if heat enters into a system, that means the system is gaining heat. Again, in heat, we say it's positive. Heat into a system, meaning the system is gaining heat. So heat supply to the system. Heat supply to a system is positive. And if the system loses heat, we say it rejects. It rejects to the surrounding. So we say heat is lost to the surrounding. And heat lost to the surrounding, we say it is negative. So heat supplied positive, heat rejected is negative. Now let's talk about working. Work into a system and work from a system. Now, what we normally do in thermodynamics is to supply heat to a system for the system to do work. For the system to do work. So from the definition, from the first definition, we said that the conversion of heat energy to work energy, the conversion of heat energy to work energy by means of a heat engine. The conversion of heat energy to work energy, thermodynamics, the conversion of heat energy to work energy. So if you supply heat, that heat must produce work. So work will be produced from the heat that you supply. So if you supply heat and that heat into a system does work, it means that the system is doing work on the surrounding. So we say it is positive. Work from a system is positive. It means that the work is done by the system. We supply heat for that system to the system for the system to do work. To do work. So the arrow goes out. So the work out of the system is work done by the system. Work done from the system. We say work done by the system on the surrounding. So it is positive. Now, if the system is gaining work or is receiving work from the surrounding, then we say it is negative. Why? Because we have to employ a certain energy, buy a certain amount of energy to supply to the system for the system to give us the work that we want it to do. So if you supply heat, work energy to the system, like when you are compressing a gas, when you compress a system, during the compression stroke of an internal combustion engine, when you compress the gas, it means that we are doing work on the system. So if you have a diagram like this, a piston cylinder arrangement like this, if you have a piston cylinder arrangement like this, and we have the piston moving from the bottom dead center to the top dead center, from the bottom dead center or outer dead center to the top dead center. This is the top, this is the bottom. Or for horizontal engine, this will be inner, this will be outer. Okay. So if you compress the gas, it means the piston is pushing the gas. It means the work the system is receiving is negative, meaning you have an external work, the surrounding, which is the piston, is doing work on the system. So we say it is negative. We supply heat to the system for the system to do work. That's the main motive. So heat supplied to the system is positive. Heat rejected by the system from the system is negative. Work done on the system is negative, and work done by the system is positive. So work done on, and this work done by. Okay, so this is the one school of thought ideology. Another school of thought also have this ideology, that Sine convention, which differs from this, but we are going to employ this throughout our calculations or throughout continuing. So the Sine convention, heat supplied is positive, heat rejected is negative, work done on the system is negative, work done by the system is positive. Now let's talk about the first law of thermodynamics. First law of thermodynamics. The first law of thermodynamics states that if a closed system is taken through a cycle, then the net work done by the system on the surrounding is proportional to the heat supplied to the system from the. So you see that the first law says that if a closed system is taken through a cycle, the net work done by the system on the surrounding is proportional to the net heat supply from the surroundings. Which means that the summation of all the work is directly proportional to summation of all the heat you supply. In other words, the work net is directly proportional to the heat net. Work net is directly proportional to heat net. But if we change this proportion sign to an equation, then we are going to have work net is equal to a constant Q net work net is equal to a constant Q net. So now this definition is from the experiment conducted by Joule. Okay, so according to Joule, the summation of work is directly proportional to the summation of heat, which means that we supply heat to do the work. And here we have the constant of proportionality here. So we say that since we have this constant of proportionality, if the summation of work or work net is equal to 1 Newton meter, that means the unit of work done is Newton meter, then we can say that since summation of work is directly proportional to summation of heat, it means that heat net or summation of heat will also be 1 joule. The unit of heat is joule, and the unit of work is Newton meter. So if heat is directly proportional, if work is directly proportional to heat, then it means that whilst work is 1 Newton meter, heat will also be 1 joule. So they should all be the same. So it means that it follows that if you substitute this information into the standard information we just derived, Q net is equal to a constant work net equal to a constant Q net. If we substitute this into that, we are going to have 1 Newton meter equal to a constant times 1 joule, which means that 1 Newton meter is equal to 1 joule. So 1 Newton meter equal to 1 joule. So the constant is going to be 1. Since this is directly proportional to this, it means that 1 Newton meter equal to 1 joule. Therefore, C is going to be 1. If you try to divide, we have 1 Newton meter over 1 joule is equal to C. But 1 Newton meter or work, net work was directly proportional to net heat. So it means that this and this has the same quantity or the same units. So it will be the same. So since they are the same, that's why they are related. So 1 joule is the same as 1 Newton meter. Then we are going to get 1 equal to C. So the constant of proportionality is equal to C. If the constant of proportionality is C, then what we are going to get is the net heat is equal to, the net work is equal to the constant, which is now 1, times the net heat. So we have Q net equal to work net. And this is the first law of thermodynamics. What the first law has given us, which can also be written as Q net minus Q net being the input minus work net being the output equal to 0. Q net being the input equal to work net being the output, because work depends on heat. Okay, so this is the first law of thermodynamics. Let's look at some few examples and apply the laws of thermodynamics to solve problems. Okay, if we take for example, now the question on the board, we have The figure below shows a certain process which undergoes a complete cycle of operations. Determine the value of the output work, WO. In other words, W out. Determine the value of the output work, W out. Now, if you look at this system, we have given heat in to the system, heat work in to the system, work out from the system, which we have to determine, and then heat from the system. Now, to solve this problem, we have to know whether the heat here is positive or negative. Heat is supplied to the system. We have to assign the signs, the sign convention, use the sign convention to help you to assist yourself to solve the problem. So let's look at this carefully. We have 10 kilojoule of heat supplied to the system, and we said that heat supplied to the system from the sign convention is positive. Let's go to the heat coming out from the system. Heat coming out from the system is negative. If heat supplied to the system is positive, heat out is negative. Now, work into the system is work done on the system. The surrounding is doing work on the system. The work done on the system. The work done on the system is negative. So it means that this work, since the arrow is going out, it should also be positive because work out is positive. So let's look at this. Okay, let's go. We can simply solve this using the first law of thermodynamics, which is summation of heat is equal to summation of work. Okay, and here we have two works, the work out and work in. We have heat in and heat out. So, and we have assigned the signs to it. Now we have summation of all the heat, which means Q in plus Q out is equal to summation of work will be work in plus work out. Heat in is positive, 10 joule, plus we can add 10 kilojoule, plus heat out is negative 3 kilojoules equal to work in is negative 2 kilojoules plus work out we don't know, unknown. So here we have to simplify this. We have 10 kilojoules of work of heat. Positive times negative will be negative 3 kilojoules equals to, we have negative here, negative, positive here times negative will be negative 2 kilojoules plus work out. And we have to make work out the subject. So we have 10 kilojoule minus 3 kilojoules. Negative 3 kilojoules comes here to become positive 2 kilojoules equal to work out. So work out is going to be 10 kilojoule minus 3 kilojoule is 7 kilojoule. 7 kilojoule plus 2 kilojoule will be 9 kilojoules. So this will be 9 kilojoules of work that is done on the surrounding. So this is work done on the surrounding. It's as simple as this. Let's look at the second example. In this example, we are given that during a complete cycle of operations, a system is subjected to the following heat transfers. The first one, 800 kilojoules supplied and 550 kilojoules rejected. At 2 points, work is done by the system to the extent of 96 kilonewton meter and 20 kilonewton meter. At a third point, there is a further work transfer. Determine its quantity and state whether it is work done by or on the system. Determine its quantity and state whether it is work done by or on the system. We can draw this system, simple system solution. We can draw this system simply as this system. Then let's go. During a complete cycle of operations, a system is subjected to the following heat transfers. 800 kilojoules supply. Heat supply 800 kilojoules. Q in 800 kilojoules. Positive. And 550 rejected. Q out or Q rejected. 550 kilojoules and it's rejected, so negative. At 2 points, there is work done by the system. At 2 points, there is work done by the system. Work done by the system. So at 2 points, there is work done by the system. This way. So we have work done by the system, work out, another work out, so work out 1, work out 2. To the extent of 96 kilonewton meter, and then 20 kilonewton meter. They are all positive because it's work done by the system. At the third point, there is a further heat transfer. Determine its quantity and state whether it is work done by or on the system. We have the third work. We don't know whether it's work done by or work done on. So there's the third work, work 3. Now let's look at this. So let's write this is still under the first law. So summation of heat is equal to summation of work. So we have Q in, we can say this is Q1 or Q in plus Q out equal to the third work. We don't know its direction, work 3, or we have work 1 plus work 2, work done 3. So heat in is 800 kilojoules. Now here we have to be careful about the units. Here we have kilojoule, and then the work we are given in kilonewton meter. And we established from the first law that 1 kilonewton meter, 1 newton meter is equal to 1 joule. So this is the same as 96 kilojoule. We similarly to 20 kilojoule. We said 1 newton meter is equal to 20. 1 newton meter is equal to 1 joule. So they are all in kilojoules. The units are all in kilojoules. So we can simplify easily. So Q out is negative positive negative 550 is equal to work 1 is work done by, so it's positive 96. Work 2 is work done by is 20 positive. And work 3 we don't know it directly, but we know we are summing, so work 3. So we want to find the work 3. So this is 800 minus 550. Now, if we bring this to the left hand side, we have minus 96. If we bring to the left hand side, we have minus 20 equal to work 3. So we have 800 minus 550 minus 96 minus 20 to compute. So finally, you get W3 to be equal to 800 minus 550. 800 minus we have 134 kilojoules. You have 134 kilojoules. And 134 kilojoules is positive. The sign here is positive. Positive 134 kilojoules. Since it is work, you can make it Newton meter. Kilo-Newton meter. Okay, fine. Alright. If you have 134 kilojoule and it is positive, it means that it is work done by the system. The question says you should state whether it is work done on the system or work done by the system. You should state whether it is work done on or by the system. So it is work done, because positive is work done by the system on the surroundings. It's work done by the system on the surrounding. Now, according to the first law of thermodynamics, we said summation of work, summation of heat minus summation of work is equal to 0. Now, we said that in the first law, summation of heat minus summation of work is equal to 0. In other parts, it can not all the heat was converted to work. So meaning we cannot get all the system to be 100% efficient. Now, so let's take, for example, in an internal combustion engine, a petrol engine or a diesel engine, when you supply petrol or diesel into the engine in a very cool state, when the diesel or petrol has burnt in the combustion chamber, now all the heat should have been converted to work, but we notice that all the heat should have been converted to work such that we should have see or get the same state of petrol at the outlet, meaning if it entered cold, it should come out cold. But we are not able to get that. So it means that not all the heat has been converted to work. So now, when the petrol enters in a cool state, it has its initial internal energy, and when it comes out as a very hot fluid, it also has its final internal energy. So we say that this change in internal energies, the initial energies, is equal to the net heat minus net work. So we say that summation of heat minus summation of work is equal to change in internal energy, which is denoted U2 minus U1. This is as a consequence of the first law of thermodynamics. So we have this formula.